You know, keeping our electrical grid stable is this huge, constant balancing act. And a massive part of that is knowing exactly how much power is going to be available at any given moment. Today, we're going to tackle that problem head-on and see how machine learning can basically give us a crystal ball for this super critical task.
So let's just frame the question right here. This isn't just some academic exercise, right? For the folks who actually operate the power grid, this is a high-stakes problem they are dealing with literally every single minute of every day. If you can answer this question accurately, it means a more stable, a more efficient, and honestly, a more reliable power supply for all of us. So how do we do it?
All right, we're going to focus on a specific type of power plant, a combined cycle power plant. Our mission, should we choose to accept it, is to take live sensor readings from the environment right around the plant and use them to predict its net hourly electrical energy output. That's a mouthful, but it's just the amount of energy it's producing measured in megawatts.
So what are we working with? Well, we've got 4 key ingredients, 4 pieces of data that are collected every single hour. We have the ambient temperature, the exhaust vacuum from the steam turbine, the ambient pressure, and the relative humidity. The goal is simple. Take these 4 inputs and predict that one crucial number, the energy output.
Now, before we start building our predictor, we need a way to keep score, right? We're going to be using something called root mean squared error, or RMSE for short. Just think of it as the average mistake our model makes with its predictions. The really important thing here is that it's measured in megawatts, the same thing we're trying to predict, and it punishes big mistakes way more than small ones. So for us, a lower RMSE is always better.
Okay, so first things first. We have to put on our detective hats. We've got this data set with over 9,500 hourly readings. Let's just dig through this data and see if we can find any clues, any patterns that tell us what's really driving this plant's energy output. And wow, when you actually look at the data, this is where it gets really interesting. These charts show how each of our ingredients relates to the energy output. And you can see some connections here and there, but just look at that top right one. Temperature versus energy output. That is not a random cloud of dots, my friends. That is an incredibly strong, super clear, downward-sloping line. This is a massive, massive clue.
And this number right here, this just hammers that point home. This is the correlation coefficient between temperature and energy output. A perfect negative relationship would be -1. We are at -0.948. I mean, we are incredibly close. This is by far the biggest signal in our entire data set. It's not even a contest.
So, what's the big takeaway from all our detective work? It's actually super simple. As the outside temperature goes up, the power plant's energy output goes down. It's this beautiful, clear, inverse relationship. And this is the core idea that we're going to ask our machine learning models to learn.
Okay, we've found our big clue. Now it's time to pick the right tool for the job. And what's the best way to do that? Well, we're going to hold a competition, a bake-off, if you will, between 5 different machine learning algorithms to see which one can give us the most accurate predictions using our data.
All right, let's meet the contenders. We've got a couple of simpler, linear models. Then we have a more complex decision tree. And finally, we've got the heavy hitters, 2 powerful ensemble models, random forest and gradient boosting. These guys basically combine the wisdom of hundreds of little decision trees to make one super smart prediction. So, let the games begin.
And the results are in. We judged every model on its average error, that RMSE score we talked about. And you can see the 2 linear models, well, they came in last. The decision tree did a bit better, but look at the top. The ensemble methods are the clear winners. And with the lowest average error of just 3.471 megawatts, Random Forest takes the crown.
So we have a champion, the Random Forest model. And it wasn't even a close fight. Its predictions had an average error that was 24% smaller than the basic linear regression model we started with. I mean, that is a huge leap in accuracy.
Okay, so our Random Forest model won the competition on the training data. But look, winning on the practice field is one thing. The real test, the thing that really matters, is how it performs on data it has never, ever seen before. So let's put it through its final exam.
And the first result from our final test is the R-squared score. And that is an absolutely incredible number. What this means is that our model can explain almost 96% of the changes, the variation, in the power plant's energy output. It means the model isn't just guessing. It has genuinely figured out what's going on.
And here it is, the bottom line, the final score. The root mean squared error on brand new data is 3.45 megawatts. In the real world, this tells us that our model's predictions are, on average, only off by about 3.45 megawatts. That's it.
Now, to put that number into perspective for you, 3.45 megawatts, that's an average error rate of less than 1% of the plant's typical output. That is a remarkably, stunningly accurate prediction. And remember, it's being made from just 4 simple environmental sensor readings.
And these charts, well, they give us the visual proof. On the left, you've got the real energy output versus what our model predicted. You see how all those dots form a super tight line? That is exactly what you want to see. And then, in the other charts, the errors themselves are just scattered randomly around 0. That tells us our model isn't consistently guessing too high or too low. It's the visual signature of a really high-quality model.
So we know the model is a rock star. We know it works incredibly well. But why? What's its secret? What did it actually learn was the most important thing for making its predictions? Let's take a peek inside the model's brain.
And here it is. I mean, wow. The model makes it incredibly clear. A staggering 90.6% of the model's entire predictive power comes from just one thing: ambient temperature. Exhaust vacuum is a distant second, and the other two barely even move the needle.
So why on earth is temperature so dominant? Well, it all comes down to some basic physics. These power plants use gas turbines, and those turbines work by compressing air. When the air outside is hotter, it's also less dense. That makes the turbine less efficient at its job, and as a result, it generates less power. Our model didn't just find a random fluke in the data, it actually rediscovered a fundamental principle of thermodynamics.
So, what's the bottom line? What does this all mean for the real world? It means that power grid operators can now use a pretty simple machine learning model fed by just a few weather sensors to forecast a power plant's output with an error margin of less than 1%. That is an incredibly powerful tool for creating a more stable and reliable energy grid for all of us.
And that kind of leaves us with one final thought. We started with thousands of data points, and we ended up with this highly accurate predictive model. So if we can do all this, if we could build a crystal ball for something as complex as a power plant, what else can we predict? What other critical systems are just waiting for us to find the right data?